Welcome to this coding walkthrough. In this session, we'll be tackling problem number 469, titled Convex Polygon. The objective of this problem is to determine whether a given polygon is convex, which is a fundamental concept in computational geometry. We'll explore different approaches to solve this problem efficiently. Let's dive in. In this problem, you are given a list of points that describe the vertices of a polygon, and your task is to determine whether the polygon is convex. The points are provided as a list of lists, where each inner list contains two integers representing the x and y coordinates of a point. A polygon is considered convex if all of its interior angles are strictly less than 180 degrees. Alternatively, you can think of it as a shape where every line segment connecting two vertices lies entirely within the polygon or on its boundary. The points are guaranteed to be provided in counterclockwise order, and the final point in the list connects back to the first point to complete the polygon. The input to the function will be a list of these points, and the output should be a Boolean value returning true if the polygon is convex and false otherwise. Let's look at an example to understand this better. Suppose the input points are 0, 0, 0, 10, 10, 10, 10, 0. These points form the vertices of a square, which is a convex polygon. All of the interior angles in this shape are 90 degrees, which are strictly less than 180 degrees. Therefore, the function should return true. Now, consider another example where the input points are 0, 0, 0, 10, 10, 10, 5, 5, 10, 0. In this case, the polygon is not convex. The inclusion of the point 5, 5 creates a self-intersecting shape, which means it no longer satisfies the convexity condition. As a result, the function returns false. To elaborate further on the second example, the issue arises because the line segment connecting 0, 10 to 10, 0 intersects with the segment connecting 10, 10 to 5, 5. This self-intersection violates the requirement that all line segments between vertices should lie entirely within the polygon. Now, let's consider another example, 1, 1, 2, 2, 2, 0, 2, 2, 1, 1. This set of points forms a convex polygon, as all the interior angles are less than 180 degrees. No segments intersect, and the shape is closed. Therefore, the function correctly returns true for this input. There are a few additional points to keep in mind. The input guarantees that the given points are unique, and they are always presented in counterclockwise order. The polygon is closed, meaning the last vertex connects back to the first. Since the number of vertices can go up to 10,000, the solution must be efficient and handle large inputs gracefully. Consider edge cases like triangles, which are always convex, and polygons with collinear points, where multiple points lie on the same straight line. It's also important to handle sharp turns correctly, ensuring the function identifies whether such turns break convexity. Finally, the solution should be robust enough to avoid overflow or precision issues when dealing with very large or very small coordinate values. To determine if a polygon is convex, we can consider a brute force approach that relies on evaluating the orientation of every triplet of consecutive points. The intuition behind this is that a polygon is convex if the orientation of all triplets is consistent, meaning either all clockwise or all counterclockwise. The orientation of 3 points can be calculated using the cross product of the vectors formed by these points. If we detect a change in the sign of the cross product for any triplet, it indicates that the polygon is not convex. This approach involves iterating through all triplets, computing their cross products, and verifying that the signs remain the same throughout. It has a time complexity of O(n), because we examine each vertex once, and it requires O(1) space. While it is simple and efficient for smaller polygons, it may struggle with degenerate cases, such as duplicate points or collinear edges, unless additional checks are implemented. A more optimized approach builds upon the brute force method by minimizing the number of calculations and introducing early termination. Instead of evaluating all triplets, we calculate the orientation for the first pair of points and use it as a reference. As we iterate through the remaining points, we check the orientation of each new triplet. If we encounter an orientation that differs from the reference, we can immediately conclude that the polygon is not convex and terminate the process early. This refinement retains the same O(n) time complexity and O(1) space complexity but avoids unnecessary calculations, making it more efficient. However, it introduces slightly more complexity in implementation. Additionally, an alternative approach involves measuring the angles between consecutive edges at each vertex. If all angles are less than 180 degrees, the polygon is convex. While this method uses a different geometric principle, it is less efficient and more computationally intensive due to the use of trigonometric calculations. To apply the angle measurement approach, we calculate the angle formed at each vertex using the dot product of consecutive edge vectors. The goal is to ensure that all angles are less than 180 degrees, which would confirm the convexity of the polygon. However, this approach has several trade-offs. The time complexity remains O(n), as we still need to evaluate each vertex, but the use of trigonometric calculations makes it computationally heavier than the cross-product method. Additionally, the reliance on floating-point arithmetic introduces the risk of precision errors, particularly when dealing with complex or large polygons. This makes the angle measurement approach less practical and harder to implement compared to the cross-product-based methods. After evaluating the different methods, we chose the brute force approach using the cross-product for several reasons. First, it is simple and robust, leveraging a fundamental and reliable geometric principle to directly determine convexity. Second, the time complexity of O(n) is optimal for this problem, as we need to evaluate all vertices at least once regardless of the approach. Third, the use of integer arithmetic in the cross-product ensures numerical stability and avoids the precision issues associated with floating-point calculations. Lastly, this approach naturally handles edge cases, such as collinear points, by identifying them through zero values in the cross-product. These factors make the brute force method both efficient and dependable for this problem. While alternative methods like angle measurement or optimized early termination strategies offer their own advantages, they come with trade-offs that make them less suitable for this specific problem. The angle measurement approach, for example, is hindered by the computational expense and potential precision errors of trigonometric calculations. The optimized brute force method improves efficiency slightly by terminating early but adds implementation complexity without a significant overall benefit. The brute force method with cross-products strikes the best balance, combining simplicity, performance, and robustness. In summary, it is the most intuitive and efficient choice for determining polygon convexity, and its reliability makes it the preferred approach for this problem. To determine if a polygon is convex, we need to ensure that all its interior angles are less than 180 degrees, or equivalently, that every turn between consecutive edges is in the same direction, either all clockwise or all counterclockwise. The algorithm begins by representing the polygon as a list of points, where each point is given as an x, y pair. These points are assumed to be provided in order, forming the boundary of the polygon. The first step is to initialize the number of vertices, n, and ensure that the polygon is valid by checking if n is at least 3. If it's not, we immediately know the polygon isn't valid. Next, we prepare a variable called prev_orientation to store the orientation of the first triplet of points. This will help us track consistency in the turning direction throughout the polygon. The orientation between 3 points is calculated using the cross-product of their vectors, which allows us to determine whether the turn is clockwise, counterclockwise, or if the points are collinear. This calculation forms the backbone of the algorithm. The orientation calculation is straightforward. For 3 points P1, P2, and P3, the cross-product of the vectors formed by these points determines the orientation. If the result is greater than 0, the points form a counterclockwise turn. If it's less than 0, the turn is clockwise. A result of 0 means the points are collinear, lying on a straight line. Now, the algorithm iterates through all triplets of consecutive points, ensuring we treat the polygon as a closed loop by using modulo arithmetic to wrap indices. For each triplet, we compute the orientation. If the points are collinear, we skip them as they don't affect the convexity check. For the first valid triplet, we initialize prev_orientation to store its orientation. As we continue iterating, we compare the orientation of each new triplet to prev_orientation. If the orientations differ in sign, indicating one turn is clockwise and another is counterclockwise, the polygon cannot be convex, and we return false. If no inconsistent orientations are found, the polygon is convex, and we return true. The consistency of turning direction across all triplets is the key insight that guarantees convexity. The cross product plays a central role here. It's a powerful tool for determining the geometric relationship between 3 points, and it allows us to efficiently check whether a triplet forms a clockwise, counterclockwise, or collinear arrangement. Using modulo arithmetic is another important aspect, as it ensures that the polygon is treated as a closed loop, with the last edge naturally connecting back to the first vertex. This way, we don't need special handling for the final edges. Additionally, collinear points are safely ignored because they don't change the overall convexity of the polygon. To implement this algorithm, we rely on simple data structures. The input is a list of points, stored as x, y pairs, which makes it easy to iterate through the vertices. We also use a single variable, prev_orientation, to track the orientation of the first valid triplet. This reduces memory overhead and keeps the implementation efficient. The algorithm itself is lightweight in terms of operations. Computing the cross product for a single triplet is an O(1) operation, and since we process each vertex exactly once, the overall complexity of the iteration remains linear in the number of vertices. The use of modulo arithmetic ensures seamless traversal of the polygon's edges without special case handling. This algorithm is highly efficient, with a time complexity of O(n), where n is the number of vertices. Each triplet of points is processed in constant time, and we iterate through the list of vertices exactly once. The space complexity is O(1), as the algorithm only uses a few variables for computation, such as prev_orientation and temporary variables for the cross-product calculation. However, there are edge cases to consider. If the polygon has fewer than 3 vertices, it's degenerate and immediately invalid. Collinear points don't affect convexity, so they're safely skipped during the orientation check. It's important to note that the algorithm assumes the input is a simple polygon, meaning it has no self-intersections. If the input violates this assumption, the result may not be reliable. Lastly, if the coordinates are given as floating point numbers, precision errors could impact the orientation calculation. This can be mitigated by using integer coordinates where possible or introducing a tolerance for comparing small values. With these considerations in mind, the algorithm is robust and performs well for determining the convexity of a simple polygon. This implementation determines if a polygon is convex by checking the cross products of consecutive edges to ensure they all have the same directional sign. We start by defining a helper function, cross_product, which computes the cross product for 3 points. This is essential for determining the relative direction, clockwise or counterclockwise, of consecutive edges. The main function, isConvex, iterates through all points in the polygon, considering 3 consecutive points at a time. The cross product is calculated for the vectors formed by these points. If the cross product is 0, the points are collinear and are ignored. Otherwise, the sign of the cross product is determined. We track the sign of the cross product using the variable prev_sign. Initially, it is 0, and we update it upon encountering the first non-zero cross product. If subsequent cross products have a different sign, the polygon is not convex, and we return false. If the iteration completes without any inconsistencies in the sign, the polygon is convex, and we return true. This algorithm ensures that the polygon's convexity is determined efficiently, iterating through the points in O(n) time, where n is the number of vertices in the polygon. Here, we have the Java implementation of the solution, starting with the method isConvex. The method takes a list of points as input, where each point is represented as a list of 2 integers for its x and y coordinates. The first step is to determine the total number of points using points.size, and initialize a variable prev_sign to 0. This variable will help us track the sign of the cross product as we iterate through the points. Next, we loop through each point in the list, and for each iteration, we select 3 consecutive points cyclically. This is achieved using modular arithmetic to ensure that the indexing wraps around to the beginning of the list when needed. Once we have these 3 points, we calculate the cross product of the vectors formed by these points using the helper method crossProduct. If the cross product is non-zero, it indicates that the points are not collinear. In this case, we determine the sign of the cross product, positive or negative, and compare it to the prev sign. If prev sign is 0, we update it to the current sign. However, if the current sign is different from the previous one, it means the polygon is not convex, and we return false. Finally, if the loop completes without any inconsistencies in the cross-product signs, we return true, indicating that the polygon is convex. Next, let's look at the cross-product helper method. This method computes the cross-product of two vectors defined by 3 points, P1, P2, and P3. First, we calculate the x and y components of the two vectors. The vector from P1 to P2 is represented by x1, y1, and the vector from P2 to P3 is represented by x2, y2. The cross product is then calculated as x1 asterisk y2, y1 asterisk x2. This result determines the orientation of the 3 points, whether they turn clockwise, counterclockwise, or are collinear. By using this helper method in the main isConvex function, we can efficiently check the orientation of consecutive points and verify if all turns are consistent, ensuring that the polygon is convex. Here, we are determining if the given points form a convex polygon. The input represents a square, which is a convex shape. First, we initialize n to the number of points, which is 4, and preb_sign to 0 since we haven't calculated any cross product yet. In the first iteration, we take 3 consecutive points, 0, 0, 4, 0, and 4, 4. Using these points, we compute the cross product as shown in the formula. The result is 16, which is positive, so we set current_sign to 1. Since preb_sign was 0, we update preb_sign to 1. This sets our baseline sign for the polygon. Next, in the second iteration, we analyze points 4, 0, 4, 4, and 0, 4. The computed cross product is again 16, and current_sign remains 1. Since this matches the preb_sign, no direction change is detected, and we continue to the next step. In the third iteration, we examine points 4, 4, 0, 4, and 0, 0. The cross product calculation gives 16, and current_sign is still 1, consistent with the preb_sign. Similarly, in the fourth iteration, using points 0, 4, 0, 0, and 4, 0, the cross product yields 16 once more. Again, current_sign is 1, and there's no change in direction. After completing all iterations, we perform a final check and see that the sign remained consistent throughout. This confirms that the polygon is convex, so the output is true. In this example, we test a non-convex polygon defined by the input points. The vertex, 2, 2, creates a concave angle, making it a non-convex shape. Starting with initialization, n is 5, and preb_sign is set to 0. In the first iteration, we use points 0, 0, 4, 0, and 2, 2. The cross product is calculated as 8, resulting in a positive sign, so current_sign is 1. Since preb_sign was 0, we update preb_sign to 1. In the second iteration, we analyze points 4, 0, 2, 2, and 4, 4. The cross product this time is -8, which is negative. This gives a current_sign of -1, indicating a direction change as preb_sign was 1. A direction change means the polygon is not convex, so the output here is false. Next, we look at an example where all points are collinear, meaning they lie on the same straight line. Since collinear points cannot form a polygon, this input is considered degenerate. Initialization sets n to 4 and preb_sign to 0. In the first iteration, we use points 0, 0, 2, 2, and 4, 4. The cross product calculation results in 0, indicating collinearity. Since there's no valid cross product, we move to the next iteration. For the second iteration, using points 2, 2, 4, 4, and 6, 6, the cross product again computes to 0, confirming that these points are collinear as well. With all iterations completed, no valid cross product was found. This means the points do not form a proper polygon, but degenerate cases like this are considered convex by definition. As a result, the output for this example is true, even though the points are collinear. This concludes our analysis of different polygon cases and how we determine convexity using the cross-product method. The time complexity of our solution can be broken down step by step. First, we have an outer loop that iterates through all the points in the polygon. If there are n points, this loop will run exactly n times. Within this loop, we calculate the cross product by calling the cross_product function. This function involves a fixed number of arithmetic operations, such as subtractions and multiplications, all of which are constant time operations, or O1. Additionally, we use modular arithmetic to access the points in a cyclic manner, ensuring that we can wrap around to the first point when needed. This operation is also O1. When we combine these components, the loop runs n times, with each iteration performing O1 work. As a result, the total time complexity is the product of these terms, which simplifies to O(n). Now, let's analyze the space complexity of the solution. The primary factor here is the storage required for the input. The points array, which contains n points, is read but not modified during the algorithm, so it uses O(n) space. Beyond the input, the algorithm utilizes a few auxiliary variables such as preb_sign, current_sign, and cross for its computations. These variables require only constant space, or O1. The cross_product function doesn't allocate any additional memory aside from its local variables, which are also constant. Since the algorithm does not rely on any extra data structures, the total space complexity is O1, excluding the input storage. Comparing this approach to a brute force method highlights its efficiency. A naive solution might involve calculating the angle between every pair of adjacent edges to ensure all angles are less than 180 degrees. This would require iterating through nested loops over the edges, leading to a time complexity of O(n²). In contrast, the optimized approach leverages the cross product to directly determine the sign of the turn formed by 3 consecutive points. This eliminates the need for more computationally expensive trigonometric calculations, reducing the time complexity to O(n). Regardless of the input, the best, average, and worst-case scenarios all result in O(n) time. Even if non-convexity is detected early, the algorithm processes at least 3 points to compute the first cross product, ensuring a linear complexity in all cases. Finally, let's solidify our understanding of the algorithm's big O notation with a mathematical perspective. The dominant factor in the algorithm is the single loop that iterates over n points. At each step, the operations performed, such as computing the cross product and using modular arithmetic, are constant time operations, or O1. As the number of points increases, the total number of operations grows linearly with n, confirming that the time complexity is O(n). Similarly, since the algorithm does not require any additional data structures and only uses a constant number of auxiliary variables, the space complexity is O1. These characteristics make the solution both efficient and scalable for larger input sizes. When working with convex polygons, there are a few common mistakes to watch out for. First, confusing convex and concave orientation is a frequent error. Remember, for a polygon to be convex, all its internal angles must be less than 180 degrees, and the orientation of all triplets of points should be consistent either all clockwise or all counterclockwise. A single inconsistent triplet does not guarantee convexity, and assuming local consistency implies global convexity can lead to incorrect results. Another common issue arises with edge cases, such as polygons that contain collinear edges where 3 points lie on the same line, or even duplicate points. These scenarios can break orientation checks because collinear points result in a zero determinant during cross-product calculations, which needs explicit handling. Lastly, some solutions fail to normalize orientation checks. For example, only verifying the orientation for the first triplet of points and assuming the same orientation applies globally is a shortcut that can lead to errors. This approach overlooks possible flips in orientation later in the sequence, which invalidates the solution. Now, let's discuss a couple of additional mistakes that can occur. Using inefficient approaches for large inputs is another pitfall. Algorithms with a time complexity of O(n²), like checking all combinations of triplets, are too slow for this problem. Instead, a single traversal of the edges in O(n) is sufficient and much more efficient. Another error involves making incorrect assumptions about the input format. For instance, assuming the points are always given in clockwise or counterclockwise order without validating the input can lead to reversed orientation checks and incorrect results. It's important to verify the input order explicitly to ensure the logic operates as intended. When solving this problem in interviews, there are some key insights and strategies to focus on. The core idea is understanding how to use vector cross-products to calculate orientation efficiently. This method is not only essential for this problem but also highly reusable in other geometry-related challenges. Additionally, many geometry problems share similar patterns, such as ensuring consistent orientation, checking for collinearity, or identifying intersections, so practicing these patterns can be invaluable. From an optimization perspective, aim to achieve an O(n) solution by traversing the edges just once, as interviewers often test your ability to improve on brute force methods. Finally, always clarify assumptions about the input during interviews. Edge cases like collinear points, self-intersecting polygons, or duplicate points can significantly affect your solution's correctness. To deepen your understanding, you can explore related problems, such as LeetCode 587, which involves constructing a convex hull, or LeetCode 149, which focuses on collinearity and edge case handling. To wrap up, let's explore some alternative approaches to solving this problem. The preferred method is using the vector cross-product. By calculating the cross-product of vectors formed by consecutive edges, you can efficiently determine orientation in O(n) time, making it ideal for handling large inputs. However, this approach requires a solid grasp of vector math. Another option is the angle-based check, where you calculate the angles between all edges and ensure they are consistently less than 180 degrees. While conceptually straightforward, this method is slower, with a time complexity of O(n squared, and is prone to floating point precision errors. A third approach involves constructing the convex hull using algorithms like Graham's scan and comparing it with the original polygon. Although effective, this solution is overkill for simple convexity checks and has a higher complexity of O(n log n). Finally, there's the brute force method, which tests all combinations of triplets for consistent orientation. While this guarantees correctness, it is computationally expensive at O(n squared, and impractical for large inputs. Each approach has trade-offs, so choose the one that best fits the problem constraints and requirements. Great job completing problem number 469, Convex Polygon. To summarize, we explored the brute force approach along with its intuition and trade-offs. Remember, mastery in computational geometry comes with practice. If you found this helpful, don't forget to like and subscribe for more coding content. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!